So we can take CO2 at ambient condition from a gas holder, which is our dome. We compress, we go to 60 bar, we cool down at 20 degree, we liquefy, and we have from 1 kilogram of CO2, we have 1 liter storage facility at 60 bar ambient condition, which is carbon steel, very cheap vessel, which make the technology very cheap and cost effective and efficient.
That was a snippet from what's on offer in the conversation this week. Stay tuned for yet another insightful conversation. Hello and welcome back to yet another episode on the Mission Shunya podcast. I'm glad that you have taken time to check a brand new episode of the show. But in case if this happens to be the first time you are tuning in, a special welcome to you. The channel has 75 plus episodes till date. You can browse the playlist on any platform that you're listening to this on, and I'm sure you will definitely like them. I have had listeners who have complimented the artworks that we have for each episode, which is also a factor that draws them to a particular episode. So if that is your route, please go ahead. A new artwork design language is now live across the channel, and it's thanks to friends at terrageneration.com. TerraGeneration is a content agency specialized in telling stories in climate, biodiversity, and sustainability. You can know more about them from the link in the show notes. Now on to the topic for this week. Batteries are the answer to address any question related to intermittency with respect to renewable energy. In fact, batteries are also an integral part of mobility, the electric vehicles. Lithium has become a sort of household name, but the lithium batteries are not generally preferred for long duration storage, because on an average they max out at 4 hours. There are technologies that can be used for longer durations, and one such technology is compressed air. However, it becomes very location specific because you need high pressure to compress air. But recently, our guest who is joining us on this episode came up with a novel solution to use CO2 as a source for the battery. Yes, the same carbon dioxide that is part of the problem. So let's hear from our guest for this show.
Hello everyone. Thank you very much, Girish, to invite me at this podcast. I'm Claudio Spadacini. I'm the CEO and founder of Energy Dome. I'm very happy to be here to talk to you about our technologies and product, the CO2 Battery and ETCC, Energy Transition Combined Cycle.
Claudio, you have been an entrepreneur and you have worked extensively in the energy sector, particularly in geothermal, waste to energy and CSP. Now, how did Energy Dome come about? And it's been like 3 years since the start of this new venture of yours. So what is the origin story like?
Yeah, as you said, I am an engineer as a background. I spent more than 25 years of my career in the energy sector. I spent time in the municipal waste gasification, and I also started other 2 ventures in the green tech, deep tech space.
Okay.
And one in the geothermal, where, with that company, I deployed more than 500 megawatt. And in that case, I was dealing, with a technology that is supply baseload power to the grid.
Okay.
But back in 2018, talking to colleagues and other people involved in the power market, I understood the big need of storage, because the energy transition is a must and is not only necessary, but is also very urgent.
Correct.
And to go to net zero, we need a very deep penetration of solar PV and wind in the grids. But those sources of energy are very much unpredictable and create a mismatch between supply and demand into the grid.
True.
And doesn't matter if you have, let's say, a 1 or 2% penetration of solar and wind, or if you have 5 or 10%, but if you reach 30, 40, or 50% penetration and above, the mismatch is becoming significant, and the solution is storage.
Correct.
And that, brought me in the position to try leveraging on my previous experience and skills to think, to have some new idea, how to store energy, because the standard in the market is pumped hydro, but pumped hydro is a nice technology, very reliable, also economical from some perspective, but is very much site dependent because you need the mountains, and you need the right geology in order to deploy that kind of technology on ground. On the other hand, there are the lithium-ion batteries, which are good, but are good normally for very short time of storage, not for long duration energy storage. So at that point in time, I started to look at some, let's say, way to try to store energy. I studied how compressed air energy storage works, how liquid air energy storage works, and I came out with this idea to use CO2 in a closed loop in a very simple process to store efficiently and cost-effective electrical energy to allow a much deeper penetration of solar and wind into the grid.
Any reason behind selecting CO2, or how did that come about?
That is a very good question indeed. And the reason, why I had the idea to use CO2 is because the CO2 can be liquefied at high pressure and ambient temperature. This peculiarity of the CO2 make the CO2 the perfect fluid to make a long-duration energy storage plant cost-competitive and very high efficiency. And I try to explain you this a bit better, just starting from how compressed air energy storage works and liquid air energy storage works.
Yeah, that'll be a good comparison for long duration storage. So what is the other technology benefit?
Compressed air energy storage is pretty simple as a concept. You take ambient air, and through a compressor, you compress the ambient air to 70 or more bars, and then after cooling down the air is stored in salt cavern normally. The point is that if you take 1 kilogram of air, let's say, which is 1 cubic meter at ambient condition, and you compress, for example, to 70 bars and cool down to ambient temperature, the volume of this 1 kilogram of air at 70 bar ambient temperature is still 12 liters, which is quite big and costs a lot of money to store that pressurized air into vessels. That is the reason why cars, to be economically feasible, need salt cavern. But again, the salt cavern have the same problem as pumped hydro, that is related to geology and is not site independent. A very, let's say, nice technology which has been introduced with the aim to solve the site dependency of compressed air energy storage has been the liquid air energy storage.
Fair.
In liquid air energy storage, if you take the same kilogram of air which at ambient condition occupy 1 cubic meter, and you compress and you cool down to minus 180 degrees C, air liquefy. And that volume, instead of being 12 liters, is only 1 liter.
Wow.
So the vessel to keep that cryogenic air, liquid air, in that vessel is very small, and that's fine. Yes, but it's cryogenic. It's minus 180 degrees.
Correct.
And this costs money. You need exotic material, and there are a lot of difficulties, in doing that. CO2 is just as liquid air, but is liquid at ambient temperature instead of minus 180 degrees. So we can take CO2 at ambient condition from a gas holder, which is our dome. We compress, we go to 60 bar, we cool down at 20 degrees, we liquefy, and we have from 1 kilogram of CO2, we have 1 liter storage facility at 60 bar ambient condition, which is carbon steel, very cheap vessel, which make the technology very cheap and cost effective and efficient.
Wow, that is really interesting, and it's good to know that it combines both the benefit of compressed air and liquid air. And you did mention about the cost benefits to an extent between CO2 storage and compressed air and liquid air. Now, was the technology and the solution, was it really straightforward, or did you face any technical challenges as you got started with this?
So when I started the company back in January 2019, I have got the idea. In February, I just filed the first patent for the technology. And then mid 2019, I started the development of the company. The process, which is at the basis of Energy Dome and is at the basis of the CO2 battery, is a very simple process because it's just compression of CO2, which is a gas very easy to be compressed from ambient pressure and temperature to medium pressure, 50-60 bar, and then cool down, store the heat in a thermal storage, and store the liquid CO2 in vessels. The process is pretty simple. The process is very well understood from skilled engineer in the process industry, in the process power plant, and has the very key and unique advantage that can be implemented with all off-the-shelf component. It means that, the Energy Dome technology, the CO2 battery, is not a product that has to research and develop new material or new component, but is just a new process which was never discovered before, which using existing component which can be purchased through tier 1 OEM all over the world, can guarantee the right performances and give the right cost competitiveness to the product. That is the reason why, starting from mid-2019, we are just now almost ready to start up our first commercial demonstration facility, which we have built in Sardinia, the big island in Italy. And just after 2 years of operation, we have a real plant, industrial scale, not a lab plant,
Wow.
which is going to be commissioned next month in Sardinia.
Wow, that's really wonderful. And it's good to know that you bring about existing products from the market ready to use and then get it ready for this technology, this kind of energy storage. And it's most interesting to know that 2.5 years is what the time it's taken for you to start from scratch to kind of have a ready to install project. That's really wonderful. Now we do see two kind of products, CO2 battery and energy transition combined cycle. So what is the difference, and are these for any particular applications or markets in general?
Yes, that is a very good question, and thank you for that. We have two products indeed, which we have developed and we are offering to the market. The CO2 battery is the product for long duration energy storage.
Okay.
This is the product which compete in the market. In that market, we have energy storage as a benchmark, the lithium-ion batteries. We are targeting to be in the market very soon. Next quarter, we will be starting to bid our system. And this is a system which is the sweet spot of this product, the CO2 battery, is energy shifting, means to shift the solar PV produced when sun shine into the hour at night when sun set, and or to use this, let's say, energy storage system to stabilize the grid. This is a battery. It makes the same like lithium-ion batteries, but for longer duration. So we can store energy ranging from 4 to 24 plus hours, while lithium-ion batteries are good normally to store up to 2, maximum 4 hours. And beyond that 4 hours, started to be really not commercially, not economically viable.
Correct.
The other product we have developed is the energy transition combined cycle. This is the same CO2 battery, the same product, which has been adapted to be combined with gas turbine technology.
Wonderful.
So there are plenty of gas turbine and gas turbine combined cycle around the world. Normally, gas turbine combined cycle are made by a gas turbine and a bottoming steam cycle. The bottoming steam cycle is efficient but very rigid, is not flexible. What we do with the ETCC is that we have a flexible combined cycle application where we can store part of the energy when the energy is very cheap in the grid, and when we need much power to feed the grid and to stabilize the grid, and the gas turbine are started to feed that electricity into the grid, the ETCC is offering to the market a combined cycle solution which reach an efficiency of almost 80% during discharge phase. Obviously, we need some energy to charge.
Correct.
But we can charge during low hours when solar PV or wind power is almost available for free or for very cheap price. And in that hour, we compress the CO2 from ambient condition and we liquefy that. But when we need to dispatch high value power into the grid, for example, when sunset, in that case, you can start the gas turbine. The gas turbine supply heat, supply power, and supply waste heat to the bottom in ETCC cycle, which combined can deliver electricity to the grid with more than 80% efficiency to power to fuel efficiency. This ETCC, from our perspective, is very interesting for the energy transition, not only for natural gas, but mainly for future hydrogen-based combined cycle gas turbine plant.
The ETCC definitely sounds very interesting, and it serves a different set of applications. And as you rightly said, as hydrogen matures, then this could be a perfect fit for that market as well. So from the CO2 battery to getting here, was it like a natural progression for your development?
Yes, this is let's say, the two products, the CO2 battery and the ETCC, are very, very much similar. The only difference is that the CO2 battery is a standalone battery, which just need an electrical connection to the grid and or electrical connection to solar PV plant, and just charge power and store power when the power is cheap, and release back power to the grid when the grid require more power. In the ETCC, the only difference is that this CO2 battery is integrated with a gas turbine which burn fuel, which can be natural gas or hydrogen,
Fair.
produce power, which feed to the grid, and release waste heat into the exhaust gases, and this waste heat into the exhaust gases is kind of a booster which is used on the CO2 battery when discharged. So it is a combination of a battery and a combined cycle. And this put together is a product which is a flexible combined cycle, which we called energy transition combined cycle because energy transition is about flexibility.
Exactly.
Energy transition is about accommodate unstable source of energy like solar PV and wind into the grid. In order to accommodate that, we need flexible tools, flexible plant to feed the grid. And this energy transition combined cycle is the perfect flexible combined cycle to accommodate the mismatch generated by solar PV and wind in the grids.
You do rightly have a product that is flexible, but even more interesting, it also brings about the modularity feature that is very natural when you look at long duration energy storage. And I believe your solutions can start from a few tens of megawatt hours and go up to a couple of hundred of megawatt hours.
Indeed, our commercial sites, which we are going to commercialize from Q2 this year, 100 megawatt hour, 200 megawatt hour, and multiple, also up to 1 gigawatt hour or more. So our two main products will be 25 megawatt power, 4-hour duration, 100 megawatt hour, or 25 megawatt, 8-hour duration, 200 megawatt hour. And those will be standard model. Like you can buy a 5 megawatt wind turbine or a 10 megawatt wind turbine. You can buy the 100 megawatt storage CO2 battery or 200 megawatt storage CO2 battery. And then you can buy 2, you can buy 4, you can buy 10, This is just modular.
Now, the most important point is about the cost when compared to compressed air or liquid air or the other long duration energy storage products that are coming. So, how is the CO2 battery going to be priced and what is the commercial viability of the solution?
This is a very good question because at the end of the story, one technology can be nice, but can be successful only if it creates value. And in the energy storage market, the benchmark in the industry are the lithium-ion batteries.
Correct.
And lithium-ion batteries project costs are in the range of $250 to $300 per megawatt hour installed basis. So in other words, if you want to buy 100 megawatt hour system with lithium-ion batteries and inverters and all what you need, that system will cost between $25 to $30 million installed basis, which is $250 to $300 per kilowatt hour.
Correct.
If you go to in the 8-hour duration, if we look to a system which is 8-hour duration, we have a total cost installed basis which is half of lithium-ion batteries, and our lifetime is double than lithium-ion batteries because lithium-ion batteries just last for 12 years, sometimes 10, sometimes a bit longer. But after that period, you have to change at least the cell because it's like your smartphone or your laptop. And we all experience that, those lithium-ion batteries are very excellent, but degrade over time,
Correct.
After 1 year, your smartphone is just, keeping the charge for almost less of the time. So that is the same. In our case, our capex are half if compared to the same size, and our lifetime is just double. And our round trip efficiency, if you take as an average, is the same. as lithium-ion batteries, because lithium-ion batteries are 85% efficiency at the beginning, but degrade over time. And after 10 years, they are just close to 70% efficiency. As an average, those are below 75% efficiency. And we are 75+% round-trip efficiency, half of the cost, double lifetime.
That's really wonderful. Claudio, now on a final note, you do have projects coming up and you did close a big round of funding recently. So what's next after the initial pilot project, initial implementation that you're going to have in Q2 of 2022? Where are the other projects coming up? I'm sure with this kind of projections that you have, there must be a lot of demand for your products. So where are the next projects coming along?
Very good question. So as we spoke before, Energy Dome is very young. We just started mid of 2019, and the execution team has been established in the beginning 2020. After only 2 years of operation, we are very close to start our first commercial demonstration facility, which is 2.5 megawatt, 4 megawatt hour in Sardinia. After that, we will be, after this commercial demonstration facility will be up and running, we will have totally de-risked the technology and we will be ready to bid our commercial solution to the market. We have plenty of potential customers which are asking already to come and see our demonstration facility, because the number we can offer on our commercial plant are really exciting and very much competitive in the market. We have potential customers coming from South America, Europe, Middle East, India, and many places which are ready to come and finalize a contract for the CO2 battery as soon as they will see the commercial demonstration facility in operation.
That's wonderful. Claudio, it's been an absolute pleasure to have you on the podcast and have this conversation and to know more about the technology. Personally, I have not followed long duration energy storage very closely, but having had this conversation, I feel like enlightened about what's happening in the sector and how CO2 battery kind of is differentiating the entire value proposition. So thanks for taking time to join me on the podcast today.
Thank you very much, Girish. It has been a really pleasure for me to meet you and to be in this podcast. Thank you very much again.
That was a wrap on the feature segment. Hope it was useful. The intent of covering such emerging technologies is to give you an idea of all the promising technologies that are getting us to a net zero carbon economy sooner. Compressed air storage has always had this advantage of cost over lithium batteries. Even for that matter, liquid air energy storage had this advantage. But there were challenges, as Claudio mentioned in the conversation. But it looks like the CO2 battery has now solved this problem. So in summary, while meeting the expectations on price for a long duration energy storage system, the CO2 battery has also solved the other challenges like requirement of suitable geology in existing systems, which makes it a big success. Hope the first projects go well and the technology delivers for the long run. The links to connect with Claudio and follow Energy Dome will be in the show notes of this episode as always. It would be great if you can spread the word about the podcast among your network. It just takes about 30 seconds or less. I will be back with yet another episode in 2 weeks' time. Until then, this is Girish Shivakumar signing off. And as always, thank you for listening.